Okay. So last time we basically stopped here. We were discussing rotational inertia, and it was part of our study of angular quantities and rotational motion as compared to translational motion, where we have linear motion and sometimes we use quantities such as x, y, v, acceleration. And here, instead of these quantities, we defined angular quantities, theta to substitute x, omega, the angular speed to substitute v, and alpha, the angular acceleration, to substitute a, which is the translational or linear acceleration. We found the relationship between omega and theta. It's just delta theta over delta t, right? I can go back to our table showing us the summary. And so we found omega to be omega 0 plus alpha t. We also defined omega to be delta theta over delta t. And we later on defined the equivalent of Newton's law for rotational motion. So we said Newton's law for a rotational motion is going to be looking like, actually, we started with the kinetic energy before going to Newton's law. We haven't talked about Newton's law yet. So we talked about kinetic energy, and we said the kinetic energy looks like this. Half I omega squared instead of half mv squared. So we substituted v with omega, and we substituted the mass with the rotational inertia. Why? Because we said the shape and the position where different points are located is going to affect how the rotation will occur. Namely, if I have points that are further from the axis of rotation, then the energy they carry is going to be more, actually. All right. Why? Because these are going to be at a larger radius. They have to go at a larger linear speed. So it makes sense for them to carry more energy than points that are closer to the axis of rotation. Does this make sense? So our rotational inertia I reflects not just the mass, but also how the mass is spread over different points of the object. And this will be reflected in none other but the location of these different points from the axis of rotation. So, well, this is the general formula for the rotational inertia. It's the sum of the mass of different points of this object times the position or the distance of these points from the axis of rotation squared. Now, for different objects of different shapes, it's going to be a bit difficult to find the sum of mi ri squared. Namely, if I have, let's say, a disk, and I will have like infinitely more different shapes, not just a disk. So you can look at all of these shapes. What I have to do is, because these have continuous distribution of mass, not just some points that I can add up, then instead of the summation of mi ri squared, I will have to do an integration. Now, this semester, I don't want you to worry about the integration, so I'm not going to ask you to derive the expressions or integrate anywhere in the exam, all right? So what I will do instead is I'll just give you the final answer. So for, let's say, a hook about the central axis, the rotational inertia is mr squared. For a cylinder, the rotational inertia is given here. For a rod rotating around an axis passing through its own axis, the rotational inertia is half mr squared. And for a rod that is rotating around an axis perpendicular to its own axis, the rotational inertia is 1 over 12 ml squared. So we will have, it's the same rod, same mass, but its expression is different because of the different axis, and thus the points have different distances from this axis, right? And so on and so forth. This table as it is given to you in the exam. We will see later how things show up, and then we're gonna solve some problems as well as examples on these. Before I move on to an example, first I will close the door because the sound is too loud here. And by the way, like I said, feel free to join online these couple weeks if you want. All right, I sent you an email stating that. Okay, so before we solve an example, I want you to know one more formula, which is the parallel axis theorem. What does it tell us? The axis of rotation, okay, for an object so if I have an axis of rotation that is around an axis parallel to an axis passing through the center of mass, then there's this relationship between them. Let me repeat. I have this object. I know its rotational inertia around its center of mass, around an axis passing through the center of mass. Let's say that axis was, so let's say I have this rod. I'll draw an example to keep things in front of you. So if this rod is uniform, its center of mass is going to be at the center, right? Okay, so I'll take this rod as an example. Let's say this rod or this cylinder is uniform. Where will its center of mass be? It's none other but the center of the cylinder itself, right? Okay, so I'll take an example to be this cylinder. Simple situation, and its center of mass is here. So I'll choose an axis passing through the center of mass. This is an axis. Let's say the rod was rotating around this axis. What is the rotational inertia of this rod in this case? Remember, to define the rotational inertia, I need to know the shape of the object and where the axis of rotation is. Because different axes will have different rotational inertia because r will be different. R, the distance to the axis, is different. So back to our figure. If I look at the table, what is the rotational inertia for a rod with the axis of rotation passing through its own axis? Yeah, so if you look at the table here, this is our case, a rod with the axis passing through its own axis. So I is half mr squared. So I'll write half mr squared. Now, the parallel axis theorem tells me if the rod is rotating now around a different axis, but this axis is parallel and at a distance d from the axis passing through the center of mass. So let's say I have an axis 2, this is axis 1, this is I1. So the parallel axis theorem tells me that the rotational inertia for any axis that is at a distance h from an axis passing through the center of mass. So this is at a distance h from an axis passing through the center of mass. Then the rotational inertia will be the rotational inertia for the axis passing through the center of mass plus the mass of the cylinder times this distance squared. So what is the rotational inertia when the axis was passing through the center of mass? What was the rotational inertia here? The axis here is passing through the COM, and I found I from the table. I can find I2 for this axis. I don't have it in the table, that's the thing, you know? So this trick will give me some additional values for the rotational inertia for axes that are not in the table, but are parallel to axes passing through the center of mass. So what's the rotational inertia when the axis was passing through the center of mass here? What was the rotational inertia when the axis of rotation was passed through the COM? What was I? Half mr squared. I'll add the mass of the cylinder and this distance. Let's say I told you this distance is 2 centimeters. And the cylinder had a radius 1 centimeter. And its mass is 100 grams. Can I find the rotational inertia? I'll just substitute 0.1 times, the radius is 0.01 plus 0.1 times. I'm adding mh squared, where h is the distance between the two axes. Makes sense? What is this distance? 2 centimeters, 0.02. I'll square these, and I can find the rotational inertia around axis 2. So if this red cylinder or rod is rotating around this axis, then its rotational inertia is the rotational inertia when it was rotating around an axis passing through the COM plus m times the distance to the new axis squared. Let's check another example, and then I'll take questions. So I have this example here. The figure shows a rigid body consisting of two particles of mass m connected by a rod of length L and negligible mass. I will definitely bring either this question in the exam or something very similar where I put different particles and I ask you to find the rotational inertia. So here I have two masses, two particles. They are a rigid body, they're just one body. So they are connected by this rod of length L, but the rod has negligible mass. So my body, okay, it's similar to, let's say, a dumbbell, but the axis is of no weight, all right? So this rod has no weight, and these two masses, they have a certain mass, and this is my whole system. Now, this body is gonna be, I want to find its rotational inertia about an axis through the center of mass perpendicular to the rod as shown. I want the rotational inertia, I want I, okay, for a case where this system is rotating around this blue axis, which is passing through the center of mass and perpendicular to the axis of the rigid body itself, all right? So if I go to the table, let's say in the exam, I just looked at the table, I don't see any case where I have two masses and the axis is here in the middle, right? I don't, yeah. This one? Okay, definitely not. Why? My system, my rigid body is made of two spheres connected by a rod. Now, this rod satisfies this situation. But this rod, they told me, what's its mass? Negligible. So it's as if it's not there. If you substitute the mass to be 0, I is 0 for this rod. So what I should look at is the two spheres rotating around this axis, which is in the middle between them. Now, these two spheres are simply points. So I can use my basic formula, I equals the sum of the mass of each point times the distance to the axis. R is the distance to the axis. I'll go back to the main formula and I can easily use this for point objects. So in point objects, I will be able to derive an expression for the rotational inertia. Whereas for disks and rings and so on, these will be given to you. So here I can use this formula. I namely have two spheres. I'll just put m1 r1 squared plus m2 r2 squared. Now, these two particles have the same mass, and what's their distance to the axis of rotation? This is the axis, it's the blue line. You can see my cursor, perfect. And this is my first mass. What's the distance from the first mass to the axis of rotation? Yeah, it's half L, where L is the distance between the two masses. So M1 is just M, and R1 is half L. M2 is also same mass, and it's also a distance half L from the center of mass. So I'll put half L here. Makes sense? All right. Now I'll just have to solve, and I can calculate the total rotational inertia for these two masses, which are at a distance half L from the axis of rotation. So this will be 1/4 ml squared plus 1/4 ml squared. And this gives me half ml squared. Makes sense? Very typical question. In the exam, I'll definitely put something like this. I might add like another mass maybe, and then I tell you these three masses find their rotational inertia, and then you'll just add up plus m3 r3 squared. R doesn't have to be the same, like this distance. Maybe it's here, and then they form a triangle, and then the distance here is this. You just find it, you know, or it's given to you, and you plug it in your formula and find the rotational inertia. Questions? Is this hard? Yes.
Miss, can you please repeat how you got 1/4 through? Can you repeat the steps?
Yeah. So I just use the basic formula for the rotational inertia, which is the sum of mi ri squared. And I have two masses. So for each mass, I put m1 r1 squared plus m2 r2 squared. What are my masses? This first sphere here, it has a mass m, so حطيت m instead of m1, and it's at a distance half L from the axis. R is the distance from m1 to the axis. Makes sense? So the distance from this mass to the axis here is half L because the two masses are connected by a rod of length L. So this whole thing has a length L. Does this make sense? The same thing for mass 2, and then I added them up. Now I also have part B. What is the rotational inertia of the body about an axis through the left end of the rod and parallel to the first axis? So now I have a new axis, which is this one. This is part B. The axis is in the left end, but it's parallel to the first one. So I can directly apply what? The theorem we took here, the parallel axis theorem. Two axes parallel to each other, one of them passing through the center of mass. The second has an unknown rotational inertia. I can find the rotational inertia of this second rod. Makes sense? Okay, so here I'll find I by using the parallel axis theorem. What does the parallel axis theorem tell me? It tells me take the rotational inertia passing through the center of mass plus mh squared, where h is the distance between the two axes. So this is ICOM plus mh squared.
Professor,
Where is, yes?
I don't
in
understand
I
the
center of mass, do we take the two particles or one particle? It's through the left
What's
only, صح?
a good point? So I, around the axis passing through the center of mass, is the rotational inertia for my whole body. My whole body is this. This is made of two spheres. They are connected by a massless rod. So this is a whole object. It's just one object of this shape. Consider it to be a
So the
dumbbell.
answer that we got in part A.
Exactly. So this is none other but I around an axis passing through the center of mass. So I'll use what I got in part A, and then this is half ml squared plus m. Okay, I have to be careful here. This m here is the total mass of the whole body. And this is not just m, it is 2m, right? My system is made of these two masses. Previously, I have quarter ml squared plus quarter ml squared, which added up to half ml squared, right? Here, the mass is the total mass of the whole body, which is going to be 2m, not just m, right? So I'll put 2m. And what is the distance between the two axes? My first axis is here. My second axis is here. So this is my first axis. This is ICOM. It is the rotational inertia around an axis passing through the center of mass. And this is I of part B, which I don't know. I'm trying to find. So what's the distance between the two axes? It's half L as well. Excellent. So I'll substitute each by half L all squared. Makes sense? And this is going to be equal to half ml squared plus ml squared. So Actually, this is going to be a quarter, so no, I added this incorrectly. Half m L squared plus 2m 1 over 4 L squared, right? 1 over 4 and 2, this is half. I got half ml squared plus half ml squared, which is ml squared. Makes sense? Okay. I'll open another slide because I want to show you another method to solve this without the parallel access theorem.
Professor,
Yes.
I didn't understand the parallel access theorem.
Yeah, I'll explain it again.
Okay, thank you, Professor.
So again, what does the parallel access theorem tell me? It tells me if I have a rotation around an axis, and this axis is not in the table, and I cannot find it by sigma m I or I squared, then I can use this theorem. I find the rotational inertia around an axis passing through the center of mass and add that up. Let me just fix my presentation. Okay, so what does the parallel access theorem tell me? Let's say I have, I'll give you another case, another example. We talked about the example of the rod. This rod, if it's rotating around this axis, if I go to the table of constants of rotational inertias, this rod has this rotational inertia, half mr squared. Do you agree, Adam?
Yes, Professor.
Do you agree that the rotational inertia is this
Yes, I
for
do.
a rod? Yeah, so for this case, it's just half mr squared. Now, the parallel access theorem tells you if now your rod is rotating around an axis which is here. So it's rotating like this, around this axis. Rather than around its own axis, it's rotating around an axis parallel to its own axis and at a distance, let's say h from this axis. So the parallel access theorem tells me that the rotational inertia around this new axis is the rotational inertia around the center of mass axis, the axis that was passing through the center of mass, plus m times the distance between the two axes squared. So I'll write that down. I here is I for an axis parallel to this axis, but passing through the center of mass, plus m times the distance squared between these two axes. So to find the rotational inertia around this axis, I will need an axis passing through the center of mass and parallel to this axis, which is this axis basically. I know the rotational inertia of this axis is half mr squared. I'll use it here. I'll add h squared, where h is the distance to the axis I'm interested in. This axis is the one I'm interested in. And now I found the rotational inertia around this new axis by adding the rotational inertia for an axis passing through the center of mass plus m times the distance between these two axes. Makes more sense?
Yes, Professor, thank you.
And in our example, we found the rotational inertia around this axis, which actually coincides to be passing through the center of mass. And the rotational inertia here turned out to be equal to half, yeah, all of it was half ml squared. To find the rotational inertia here, I said it's going to be I, when the axis was passing through the center of mass, plus mh squared. This is the parallel access theorem. When it was passing through the center of mass, the axis gave a rotational inertia half ml squared. I'll add, okay, the mass is 2m. I have two spheres in this system. And h is the distance between the two axes. The axis of interest, which is here, and the axis passing through the center of mass, which is over here. Now the distance between these two is how much? It is half L. So I'll put half L squared. This gave me half ml squared plus 2m into quarter L squared, which is ml squared. Now, by the way, I could have solved part B using the same method of part A. So look at part B. I'm interested in this blue axis. Can I use the same formula I used in part A, which is I equals sigma mi ri squared, right? I have two spheres. The first sphere is here at the left, and the second is over here. I'll put m1 r1 squared plus m2 r2 squared. Now, m1, what is its distance to this axis? What is the distance between this mass and this axis? 0. So I'll put actually here m into 0 plus the second mass. What is its distance to the new axis here? L plus ml squared. The final answer is ml squared. Does it match with what I got from the parallel axis theorem? Yeah, same answer. So here, using parallel axis theorem, I got this answer, and my second method, I get the same answer. Any questions?
Professor, which
Okay.
one is easier? Like, which one would you use? Which one should I
Up
use?
to you. Both give you the correct answer. And I can see that both are the same difficulty to me, right?
Oh, okay.
It's just whichever occurs to you to use first.
Okay, thank you, Professor.
Any questions on these? Okay, so to me, as far as difficult as this would go, is simply I would give you a system of multiple particles, as I did here. Here I had two particles. I'd give you two particles. I'll tell you find the rotational inertia, and then I will tell you use the parallel axis theorem to find the rotational inertia around some other axis parallel to the first axis. Okay, I think that's as hard as I would take it. What I will work on next is a new quantity called the torque. This is a quantity that will tell us whether a force is going to make a rotation or no. We have talked about rotational motion and its kinematics. Next, we study dynamics, which is the causes of rotation. What will cause a rotation? Will a force always cause a rotation or no? Namely, if you look at these two figures, I have two wheels. I apply a force over here tangent to the wheel. Do you think the wheel will rotate? Yeah, you push it, you push along the edge, it rotates. What if I push down on the wheel? Would the wheel rotate? No. So actually, a force will not always cause a rotation. That's my first comment. A force will not always cause a rotation. Namely here, when I applied a downward force, there was no rotation. When I applied a tangent force, there was a rotation. In fact, for a force to make a rotation, it should always have a tangential part to the circular motion or the rotational motion. Now, to determine whether a force will make a rotation or no, I will define the torque. The torque is a quantity that will tell us whether a force results in a rotation or not. Now here there will be three factors that will determine whether I have rotation or no. One, to have rotation, definitely I should apply a force, right? No force, no rotation. An object will not rotate by itself. I have to exert a force on it. Now, will this force always make rotation? No, I have two more factors to worry about. One, what was the factor that made rotation and then did not here? What's the difference between the two cases? Is it a magnitude? It's a direction. The direction is our second factor. So there should be a force, but it should be directed. It was not. So my second factor, so one, the torque should depend on the force. There should be a force. And two, it will depend on direction. What's the math quantity I associate with directions? If I want to write down direction, the direction of a force, how did I define it? What did I find? I find an angle. Yes, exactly. So my second factor is the angle theta. Excellent. I still have one more factor. Let me see if I have an animation to show you. No. So here I'm showing actually the two factors we talked about so far. One, I make a stronger force, I get a stronger torque. The torque will have this symbol tau. Here, I am changing the direction of my force. As I change the direction, in fact, it becomes, when you want to actually rotate an object, you always feel it's easier to go perpendicular to that, to the axis of this object, right? So for example, I want to open the door. If I exert a force, which is perpendicular, it's easier than if I exert a force that is oblique. Here, you feel it's harder to rotate, right? If I'm oblique, and even if I become parallel to the whole door, I can no longer exert a rotation. So it's easier to go perpendicular to the door. This makes the rotation easier. So the direction is best when I'm perpendicular here. We're gonna see it soon. So now my last factor is actually, again, none other but the distance r to the axis of rotation. I'm trying to rotate the table here. The best thing to do is, one, make my rotation perpendicular. If my rotation is like this, my direction is different and not perpendicular, it becomes harder and harder to rotate. My second factor is be as far as possible from the axis of rotation. Where is my axis of rotation here, by the way? It's this rod. It's basically where the hinges are, usually. The door, same thing. Look at where the hinges are. I rotate around this axis. The further I am from the axis, the stronger the rotation. This distance, I will name it r, the lever distance or the distance to the axis of rotation. If I try to push from here, I need more force than when I push from here. Why? Because rotation is stronger the further you are from the axis. If I am at the axis, I try to push here. Does it rotate? No. R is 0, then the torque is 0. So now I have my formula for the torque. Look at it here. The torque will depend on the force, R, which is the distance to the axis of rotation, and phi here, or theta, or the angle, is the angle between these two, actually, between R and my force. And take a look at that. I'm applying my force here. This is R, right? This is my force. When F is perpendicular to R, as I'm doing now, what's the angle one if my force is perpendicular to R? The angle is 90, exactly. And what is sine 90? 1, which is the maximum. If my force is parallel to R, I apply a force here, no rotation. What's the angle when my force is parallel to R? It's 0, okay? And sine 0 is 0, no rotation. So I put a sine instead of a cosine, and theta is the angle between F and R. This is the definition of the torque. It is equal to the force times the distance times sine phi. In math, what is F? I didn't define that for you. Have you ever taken in math a vector W, which is u, v, sine theta? Have you seen this before in math? Have you seen a cross product? Did you in math? Who hasn't seen a cross product? Yeah, so this cross product, its magnitude is UV sine theta. I didn't take that
Yes,
when you took the
Professor.
cross product. Yes, Remy?
I was just saying that is actually UV sine theta. Yes, I was confirming.
Yeah, in all cases, we repeat it again, so don't worry. Yeah. Okay. So I have defined this torque, which is now my substitute for the force. And what's nicer now, I will define Newton's second law for rotation, which will include, of course, the torque instead of the force. And look at my formula. Instead of F equals ma, I substitute the force by what? The torque. Instead of F net, I will study the net torque. Of course, when I say net torque, this will be the torque exerted by the first force acting on the body plus the torque exerted by the second force plus the torque exerted by the third force. So if I have, let's say, a simple case, let's say I have the wheel. The wheel that we saw earlier, what are the forces acting on it? Let's say I am pushing the wheel by a force here. What other forces do we have? Weight, definitely. And what else? Maybe there's some friction. Excellent. What's the direction of friction? It will oppose the motion. Now, the wheel here is going to try to rotate. It's going to try to move to the left because of this force, but the friction will push it back to the right.
You're right.
Yeah. If it's frictionless, then I will not draw any friction. Any other forces? I have a normal force. Excellent. If I want to find the net torque and then deduce if the wheel will rotate or not, I will have to find the torque by each of these forces. So namely, I'll write tau net equals tau of the applied force plus tau of the normal force plus, so the torque, its mass symbol is tau, similar to how the angle, its symbol is this theta or alpha or phi. So tau of W plus tau of the friction force. I have to add all of these up. If the net torque is non-zero, then rotation will start. Yes. I don't think
Professor?
so.
Are we not supposed to divide it into components like the x component and the y component before calculating the net torque?
Maybe you're right. Because this torque will be clockwise. I'm not sure. Let me look up forces on a wheel. Okay, one thing you're right about, because in my, well, in real life, the friction is what moves the wheel from the first place, right? In real life, it's the friction that moves the wheel. There isn't really an applied force here. But what I will do is, yeah, maybe if I go on with this force works here like this. So maybe the friction is to the left. Yeah. I'll check it out more. If I have this applied force here, what would be the case of the friction here? But in real life, what's happening is you push on the pedal and then the friction is what makes the rotation. It's as if you're trying to push linearly, the friction forces the rotation. Anyway, not a big deal. So I'm gonna find the torque for each of these cases. How do I find the torque for the applied force? I'll put F times R times sine the angle between them. This is F. Where is the axis of rotation? The wheel is rotating around itself. So the axis is passing through its center. I'll draw the axis of rotation to keep it in front of me. Here it is. This is the axis of rotation. Now, my figure is three-dimensional. It will be a bit tricky to see the angles correctly. But for my first force, for the applied force, this is R, right? The distance to the axis. What's the angle between F and R? What's the angle between F and R here? It's 90. Is that good? 90 is good for rotation because sine 90 is 1. So that's good. I'll add the torque of the normal. This is the normal force. Now, one thing you will see about the normal is that it is actually passing through the axis of rotation. What's the angle between the, so if I write down my formula NR, what is the angle between the normal and R? This is the normal, and R is the distance to the axis. What's the angle between them? 0. The normal will not make any rotation. I'll add the weight force, WR sine, weight is downward, R is upward. What's the angle between them? 180, which will also be 0. I'll add the torque of the friction force. For the friction is in this direction. R is up, the angle is 90. Now, one thing I know is the friction and the applied force, are they supporting each other when they rotate the wheel? Let's take a look. The applied force will try to rotate the wheel clockwise or counterclockwise. So if I push like this, the wheel will rotate like this, right? Which is counterclockwise. So when I apply this force, the wheel is gonna rotate like this, which is counterclockwise. So look at the sense, you know? Whereas the friction, if it pushes the wheel back, it will try to rotate it in this direction, which is clockwise. So they are making opposite sense of rotation. So they should have opposite signs. What we will do is we will say counterclockwise rotation is due to a positive torque. All right. So my applied force, just a second. Yes.
So did we consider the friction to the right or to the left?
I said it to the left, but I'm gonna read more whether it's gonna be to the left or to the right. All right.
Okay.
Yeah. Namely, in when you're really moving real wheels, it's the friction itself that's there. There isn't this applied force. Okay, so I associated a negative sign to the torque of the friction and a positive sign to the applied force. Does this make sense? Because one is making a clockwise rotation, the other is making a counterclockwise rotation. And now I'll just, and this will give me 0, right? For the weight and the normal, these don't contribute to the rotation. So I'll get FR minus small fr. If these add up to some non-zero value, then I have some rotation. And I will say, instead of F net equals MA, I'll write tau net to be none other but I times alpha. Okay, where I is the rotational inertia, it will always substitute the mass in rotational motion. And alpha is the angular acceleration, which always substitutes the translational acceleration. Any questions? Yeah. Okay. Well, I'm not even sure of it. So next time I'll let you know. Yeah. We'll talk about it later. It's another way to find the torque by doing the cross product of F and R. All right. Yeah. Okay. Thank you for joining me today. I'll see you next time.
Professor,
Yes, Muhammad.
please can I stay a bit longer just to talk to you about something, please? If
Like
you're
Muhammad.